Yeah. Okay. Yeah. Yeah. So this problem, there's like a way of creating a tree by connecting each node to some random node that was previously there. And then you choose the permutation and like relabel everything, right? Yeah. And then you want to find the probability that this this process generates a tree that's given us input, right? Um, yeah. So how about instead, like you can consider fixing the permutation, right? Yeah, so just fix the permutation, like P1, P2, all the way up to Pn, right? So you fix the permutation and then consider like what trees can be built from this, right? So P1 has to be here, right? P1 has to exist, of course. Um, and then P2 has to be connected to P1, right? Yeah, and then P3 has to be connected to one of these two, right? It gets connected to one of these with equal probability. And then P4 has to get connected with one of these. It gets connected with equal probability, right? Right. So one thing that you can notice is yeah, so like if your permutations like 3, 2, 1, 4 or something, yeah, if your permutations like that, then something like 1, 3, 2, 4. Wait, that's valid. Wait. Okay, 2, 1, 3, 4. A tree like this is never going to be valid because from this structure over here, P2 has to be adjacent to P1, right? So given this fixed permutation, there are some trees that will never work, right? But another thing to observe is these are all distinct, right? So all of the possible trees are going to have come up with equal probability, right? So there's like, given a permutation, there's like n minus 1 factorial trees. So each comes with equal probability for each, right? Yeah, so yeah, another way to write this is like if you fix this permutation, then the probability that the tree is valid, given the permutation, is either going to be 1 divided by n minus 1 factorial, if the permutation is valid, right? Um, if the permutation is valid, probably it's going to be this, or it's going to be 0 otherwise, right? So what this tells you is the answer is going to be, if you know the number of valid permutations, then that's enough to know the answer, right? So the answer is going to be the number of valid permutations times 1 over n minus 1 factorial times 1 over n factorial, right? Yeah, so the answer is going to be a number of valid permutations times n minus 1 over n minus 1 factorial times 1 over n factorial, right? So it suffices to just count the number of valid permutations, right? Yeah, so let's look at this process again, right? We link P2 to P1, and then we link P3 to some earlier neighbor of that, right? And we link P4 to some earlier neighbor, right? So if I just draw like the tree given in the input, let's just consider what could be the valid permutations, right? Um, so this is the input. Let's say the input looks like this. Yeah. So an example of some valid permutation is maybe we pick P1 to be this, and then P2 to be this one, and then P3 to be this one, and then P4 to be here. Yeah, and then P5 here. The key thing is like when we're setting the new element, we're making it adjacent to one of the earlier elements, right? And then P6 over here. Uh, because it's adjacent to P2, and then P7 over here, P8 over here, P9 over here, right? So one way we can think of this process is we're picking a location to be the first element of the permutation, and then we keep picking some element that's next to this, right? Um, and that's like how you calculate construct a valid permutation, right? So now let's look at how to actually count the number of valid permutations. Yeah. So let's just say let's just assume we put the first element of the permutation at the root, right? So this is the tree. Let's say this is the tree. Uh, yeah. So it's like this. Let's say we decide to put the first yeah the first element of the permutation here, right? And now we get like three subproblems, right? So this is kind of looks like some kind of subtree DP. Except it's a bit weird, right? Um, like if we just have this is U and then this is V1, V2, V3, and then we let DPU equal to the product over children V of DPV. Um, this won't quite work. Like what this product counts is the number of ways to set P1 here, and then create a permutation for the left one, and then create a permutation from this one, and then create a permutation from this one, right? But it's also possible that we first add something here, and then we add something here, right? So this product is not really taking that as possibilities, right? But we can just make a small fix to this, right? So basically, the number of ways to make something in the subtrees just like multiply those. And then you also need to consider the number of ways to interleave them, right? So let's just say this is subtree A, this is subtree B, subtree C. Let's say our permutation is like maybe we decide to expand in subtree A, and then maybe we expand like two nodes in subtree B, and then we expand another node in subtree C, and then we keep expanding like that, right? Right. Then we'll actually get we'll get a different kind of recurrence. Uh, yeah, so we will get this recurrence DPU is equal to product over V child, just like before, of DPV times the number of ways to like interleave them, right? So there's going to be times the subtree, basically there's subtree size of U minus 1 factorial elements. Yeah, so times sub, like I'll just call it size U, that's the subtree size. So size U minus 1 factorial. Factorial divided by like yeah, the product of the factorials of the children. So product over V child of size V factorial, right? Um yeah. So this works for DP. Yeah, so this gives you the number of ways. If you calculate this DP, then this gives you the number of ways to yeah, uh yeah, this gives you the number of permutations where the first element starts at a root, right? And this is linear time for a fixed root. So if you take a look at the subtasks, um, you can get like like basically the first half of the points with the n squared algorithm. So to get up to like subtask 9, you can just do this n times, right? Yeah, I'll go over how to do the full task in a bit, but any questions about yeah, this DP over here, how to account for a fixed root? Yeah, so to summarize, yeah, we're trying to calculate the number of valid permutations. And you can think of a valid permutation as starting somewhere and then like expanding by picking some kind of neighbor in your tree, right? And if you start at the root, then yeah, you can do this in O of n. Um, the DP is basically a product of the children. It's DPs times the number of ways to interleave the operations in those children, right? Yeah. Okay, let's go over the full task. Yeah, so the solution to full task is based on this idea, but you have to solve for all roots. So I think informally, or it's probably commonly referred to as rerouting. But yeah, I'll go over the solution for that. Yeah, right. Uh, yeah. So we defined like in our original in the solution over here, we defined the DP just over the subproblem of the subtree that's rooted at U, right? Right. But starting at U, we might also need to consider the stuff above it, right? So we need our DP to like account for that, right? So let's just have two DPs. One is DP up, or sorry, one is DP down, which is just the same subtree DP, right? So I'll just write that. So DP down of U, which is just over the subtree, and then the other one is DP up, right? So we already know how to do this. It's basically what I explained over here. Now let's talk about how to calculate DP up, right? Maybe there are like many ways to do it. But yeah, I'll talk about one. It took a while. It took like some time to actually like yeah, think about like how the details fit in. That's probably the yeah, I think like one part of the problem is knowing like being familiar with like 3DP rerouting. And another part of the problem is like actually like getting the details correct, right? Yeah, so for DP up, uh, yeah, okay, yeah, I'll talk about how to calculate DP up. So this is U, this is like the subtree of U, and then let's say P is the parent of U, right? Um, yeah, and then this is like everything else. I'll just draw it like, wait, do I have a better drawing? Yeah, I drew a picture right before this. Okay. Um, yeah, yeah, let's say that this is the rest of the tree. Yeah, and let's say these are the other subtrees of P, right? Yeah, okay. So what I mean by DP up is the problem over here, where you're considering the problem over all of the tree, excluding the children of U, right? So this is what I mean by DP up. And once you actually have DP up, then the answer is going to be the sum over U. Uh, so the contribution of like the first element being at U is going to be sum over U of, so you have like two independent problems, whatever is above and then whatever is below, right? So it's going to be sum over U of, yeah, DP up U. So DP up of U basically has these components and then you have to divide, you have to multiply by like the factorial of all of this. So it's going to be n minus size U minus 1 factorial times uh, dp down U divided by size U minus 1 factorial. And since we like divided the sizes of everything, then we need to like multiply back the size of the whole thing. So it's going to be times n minus 1 factorial, right? So if you've calculated dp up and dp down, then the answer is going to have this form, right? So now let's talk about how to calculate dp up, right? Um, yeah, so we want to calculate dp for this, right? And then dp up of p is basically this green region over here, right? So I'll just label this as dp up of p. And then there's also like these subtrees we care about. So we can look at dp down of p, right? But we also need to ignore this subtree, right? And we only care about like these subtrees, right? Um, yeah, and then also like when calculating dp down, you had to like multiply by size factorial. So we're going to like divide that out first, right? Yeah, so this is kind of going to be like slightly involved. Yeah, so dp up of u is going to be dp down of P divide divided by like the size factorial. So size P minus 1 factorial times uh and we need to like remove this the contribution of this, right? So it's going to be times size U factorial over yeah uh wait um yeah over dp down U. Yeah, I think there's like a lot of details to actually like come up with this, but yeah um so that's like the contribution of whatever is below, and then the contribution of whatever is above is dp up p divided by um so dp up of p divided by the size of everything above p. So n minus size p minus 1 factorial. Um, and then, yeah, so once you have like all the denominators, then you need to multiply the numerator back. So the numerator is going to be like the size of everything up here, like excluding, um, yeah, excluding u and p, right? So it's going to be times uh, n minus, uh, hold up, yeah, wait, um, I think yeah, it should be n minus size u minus 1. Yeah, factorial. Yeah, yeah. Um, yeah, so that's how you calculate this. Any questions? Yeah, so the high level idea is like you can calculate the DP for the subproblem that's above the tree, um, based on like the subproblem that's above you, right? And how the implementation actually works is for DP down, this part is straightforward. You can just calculate them bottom up in a DFS, and then you can do a second DFS to calculate DP up by going from top to bottom, right? Yeah, I'll just show like the implementation I had. Okay, let me clear this. Yeah, yeah. So DP down. Yeah. Um, yeah. I guess you're not allowed to use templates in USACO, so I just wrote my own like binary exponentiation and like modular inverse, right? Yeah, and yeah, I think my implementation I also store like the size of everything above. I guess that's your personal preference. Yeah. And then yeah, one DFS to calculate the DP of all the subtrees, and then one DFS to calculate the DP of everything above, right? And this kind of has like the terms that I discussed, right? So the contribution of everything that's below and the contribution of everything that's above. I need to like divide the factorials and then multiply this factorial back again, right? Yeah, and then based on the DP up and DP down, you can it'll have some contribution to the answer, right? And then once you have the total number of good permutations, then it's just going to be yeah, the the probability is just going to be that times n like 1 over n factorial times 1 over n minus 1 factorial, right? So whenever it's a good permutation, then there's a 1 over n minus 1 factorial probability that the tree is valid. Okay, cool. Uh, yeah, any questions? Um, yeah, so I think yeah, I'll just give my personal take about this. Yeah, I think yeah, for me personally, I think like problem two, maybe it like depends. Uh, Maybe because I've done a lot of shortest path problems before, but I felt like problem two was like read the statement and implement. Or I feel like there wasn't too much to observe. Problem three, I think like the idea, uh, like of like the path to get to the solution is like pretty do or I think like it didn't take me that long to come up with like an idea of what the solution would look like, right? You're just counting valid permutations. But yeah, the details, like the actual details of like calculating the number of like doing all the rerouting and calculating the number of ways to do it is a little bit tricky and takes work. Um, yeah. Uh, yeah, I did problem one last just because yeah, I figured out problem two and three earlier. Yeah, but yeah, in retrospect, yeah. So I think like calculating the number of inversions is a pretty standard thing. Yeah. And I guess the harder part is like calculating F of P over all the shifts. Okay. Yeah, I'll just leave. Yeah, I write comments in my code because I get lost otherwise. Cool. Yeah, I'll just stay here for a few more minutes if you guys have any questions. Oh, can you share a similar problem to P3? Yeah, I finished explaining them already. I guess problem two, I don't know. Kind of, I feel like yeah, it's pretty similar to other shortest path problems. Um, wait, let me think if there's something similar to P3. Oops, wait. Okay, so I think like once when I taught a class, or not like the exact rerouting thing, but when I taught a class, I think I asked some question like, wait, or it's like pretty similar. Like, so wait, wait, let me try to remember. Maybe just like count the number of valid binary search trees. Wait, actually, wait. No, I don't even remember what the problem was. Wait, since we have time, I probably have like some time to pull it up. I think I should be able to pull it up fast. But in general, like there's also a lot of rerouting problems. I can send some links to those. Was it from Spring? Um, Give me a sec. Oh, maybe it was game routes. No. Um, okay, I can't. Wait, wait, just give me a sec. Uh, Wait, I think I did that in summer 2023 as a while back. Actually, I'm not sure. Oh, it might have been distance and tree. There was this problem. Yeah, I think there was also like another rerouting problem, which was kind of non-trivial. Yeah, but this is one. But I think like I forgot the exact problem, but the idea of this DP where you multiply your subtrees and then you consider the number of ways to interleave things. This is like a problem that I went over in one class. Yeah, yeah. Yeah, I'll just stay here if anyone has any more questions. Yeah, otherwise we're finished. Personally for me, this was much easier than normal, but um, I think like how well you do on this contest, or at least for me, I think the reason I found this easy was because I've seen a lot of similar problems. Um, like I think, yeah, and they were also like not too bad to implement. Like the last USACO Gold contest, I thought that was pretty hard because there's like the functional graph problem three that had so many steps to implement, and it took up so much time. But I didn't see any problems like that in this one. Yeah, but I did I would personally say that like this month's silver was not easy. It took me a while to come up with like the observations to do those problems. Oh, are you asking me? Uh, oh, I actually didn't do USACO in high school. I started competitive programming in college. Yeah, yeah. Oh, yeah. I mean, technically, yeah, yeah. I mean, I guess I technically in the platinum division, I passed gold. Yeah. So I think like personally, in my opinion, at least for gold, there's like a lot of variance in the problems. So I think like one thing that's important, like one thing that's useful to have is just like knowledge of gold level topics. So I think this contest is an example where like knowledge of like the topics was pretty helpful. Like I guess like tree problems, and then problem two is like some kind of shortest path problem that comes up pretty often and is kind of standard. So if you have experience doing these kinds of problems, I think I linked something similar to this. I also linked some rerouting problem for uh, problem three. Um, so I think like part of it, uh, okay, uh, I think wait, Kyle, I think your question is debatable. I'll get to that in a bit. But I think part of like doing well in gold is about just like having goal level knowledge. And then the other part is like being able to like come up with solutions to problems, solving them fast, and having good consistency is useful. But like when I did competitive programming, I used to do a lot of code forces. So I think I think like rather than having an aim to pass a level, just like having good consistency is useful. And yeah, just like doing code forces contests regularly and like upsolving like maybe one problem that you weren't able to get in contest. Um, I think that's like a good way to develop consistency. Yeah. Uh, yeah. I personally think it boils down to like having more experience. Or at least for this this contest specifically, like I felt a lot of the problems are things that have like they involve like similar techniques or ideas to similar problems that show other problems that show up. Um, yeah. But I think in general, like good advice is just like do contests regularly. And yeah, make sure you upsolve things that you weren't able to solve. Um, okay, Kyle asked, silver to gold is the biggest jump in difficulty. Is that true? I think it depends. Like, I think passing silver itself, is depending on the contest can be very hard. Uh, I've had some students who like are like they don't pass silver like the first contest, and then like after a few contests they pass gold. So yeah, I don't think there's like yeah, and also like that combined with the fact I felt like this contest gold felt much easier than this contest silver, but that might just be my opinion. Yeah. Oh yeah, I think USACO is trying to like uh yeah, I think that's like what uh, yeah, in case you're like in like a like LLM or GPT. Maybe that's like one of the t strategies are trying to reduce that. Yeah, I don't know if it's true, but I heard like a lot of people they just like copy paste that into GPT and then they don't check. Um, they like yeah, they just submit. Um, yeah, yeah, yeah. LLMs are much better than me. A lot of competitive programming problems. Yeah, I can confirm. Okay, I have to go to another Zoom call. But yeah, thanks everyone.